part 2 of our special two-part SAR webinar. This webinar is entitled Applications of SAR Data in GIS Environments. This is your host, Jennifer Brennan. I've got 2 p.m. Eastern Daylight Savings Time, so we're going to go ahead and get started here. First, what I'll do is go over a few webinar logistics. To ensure the best audio experience, participants have been placed in silent mode. But if you have any issues or you have any questions, please enter those into the Q&A pod, and you'll see that located on the lower right-hand side of your screen. This works like a chat. Today's webinar is being recorded. The recording will be posted to our online Adobe Connect webinar catalog, as well as to our NASA Earth Data YouTube channel within a few days of completion. It's my intent to complete both the first and the second part of this webinar for posting tomorrow. And when I do that, I'll send an email to all registrants with both recording links. As far as timing is concerned, today's webinar will be 1 hour long with 45 minutes allocated to the presentation and live demonstrations, and then an additional 15 minutes for the question and answer period. Our speaker today is Heidi Christensen. She is a GIS specialist at the Alaska Satellite Facility Distributed Active Archive Center, or ASF-DAC. After she has finished with her presentation, what we'll do next is we'll move to a final optional set of polling questions. And then generally, we give these questions about 3 to 4 minutes or so. And from there, we'll transition directly to the Q&A, which follows the polling period. Depending upon the volume of questions that we receive, we will extend the Q&A period an additional 15 minutes from end time for those of you who may wish to stay on the line, but we will have a hard cutoff of 3:15 p.m. So I've pulled up today's agenda. Hopefully everybody can see that. Heidi will begin today's webinar with a review of SAR concepts and an overview of today's demonstration. And then from there, we will transition to our live demonstrations that will focus on SAR scale conversions, inundation mapping, and RTC reclassification, and also log difference calculations for change detection. With that, it is my pleasure to introduce today's speaker, Heidi Christensen. Heidi?
Thank you for the introduction, Jennifer. On Tuesday, I went over the basics of SAR datasets, and today I'd like to do a bit of a deeper dive and actually make use of some of these datasets. As Jennifer mentioned, if you missed the first webinar, don't worry, it will be posted, the recording will be posted, and you can catch up on that information if you'd like. I won't go over again most of the information that I went over on Tuesday, but I do want to touch on a few quick key concepts of SAR before we move on to the demonstration. First of all, SAR signals can pass through most clouds and smoke cover, so this makes it a really useful tool for mapping the surface of the Earth during natural disasters, such as hurricanes or wildfires, events where there's heavy cloud or smoke cover that many other sensors can't actually see through. SAR data is comprised of 2 different components, amplitude and phase. The amplitude is the amount of backscatter that returns to the radar sensor, and the phase is an indication of the distance between the sensor and the Earth. Today we'll be focusing on the amplitude part of SAR datasets. Different SAR sensors can be set up to collect data in different polarizations, and there are different wavelengths that are used for different SAR sensors. And it's important to know which wavelength was used to acquire your dataset, because different wavelengths will tell you different things about the Earth's surface. Longer wavelengths, such as L-band wavelengths, can penetrate more deeply into canopy and into the soil surface, so the returns that you're getting are from further down in the canopy or even the forest floor, and then also further down in the soil layer. So if you're trying to compare L-band and C-band data, you're comparing 2 different data sets. Backscatter results are impacted both by the dielectric and the physical properties of the scatterers they interact with. The dielectric properties are the permittivity of scatterers. So if an object has a high dielectric constant, it's more likely to reflect more of the signal, whereas objects with low dielectric properties can absorb more of the signal, and there is less of it available to be returned to the sensor. different polarizations interact differently with the physical properties of the scatterers on the Earth's surface. So for example, VV polarization, or with a vertical send and vertical receive, is most sensitive to surface roughness. So if there's a smooth surface, you'll get much less return than if there's a rough surface. The backscatter will be brighter from rough surfaces than smooth surfaces. For cross polarizations, such as VH or HV, that indicates an interaction with a volume scatterer, such as vegetation. So if you get high returns in the VH polarization, that generally indicates the presence of forest or some other vegetation. SAR is acquired using a side-looking geometry, and this is really key. It's necessary in order to process the data, but it also means that there are distortions inherent to SAR datasets that need to be considered. And this is particularly important in areas that have a lot of different terrain, so mountains or rough surfaces. We need to correct these datasets before we can successfully use them in a GIS environment. The data we'll be looking at today was collected by the Sentinel-1 mission, which is a European Space Agency mission that has global coverage with 2 satellites in the constellation. It's free to access. You can download it directly from ASF's Vertex data search portal, and there's a 6-day repeat cycle for imaging. A quick reminder about radiometric terrain correction. This uses a digital elevation model to correct for those distortions that you find in SAR datasets. So it both matches the features in the SAR image to actual landscape features and also adjusts the radiometric returns so that they are representative of the appropriate surface area instead of being compressed into one small band. The RTC datasets that we'll be working with today were generated using ASF's HYPE platform, which is a beta software platform that makes use of cloud computing. SAR is a very large data set, and it can take a lot of memory and processing power to produce products. So our platform is beta, but if you're interested in giving it a try, you can visit our website. The link is listed in the persistent pods, or the persistent links pod in Adobe Connect. You can visit our HYPE website and it will direct you to contact our user services office who can set you up with an account. If you provide feedback, you have a quota to process a certain number of granules each month. And there are a number of different processes that are available on this platform. There's RTC and also InSAR, as well as a number of other products. The particular product we'll be looking at today is the RTC Gamma product. So this is generated using Gamma software, which is a commercial SAR processing software. If you download a product from HYPE, you get a zip archive that has lots of different files. The actual RTC files, there is a single geotiff for each polarization available for your product. So the files of interest are the vh.tiff and the vv.tiff, but there's a lot of other information in there. If you're new to HYPE products, I encourage you to look at the README file, which goes through each one of the layers that's included and gives you a description of what it is and what you would use it for. So that's just a text file that you can look at and get a sense of what's included. In addition, every raster that's included in the zip file has an XML file. And if you're an ArcGIS user, these XML files are readable through the item description if you're using ArcMap, or the metadata tab if you're using ArcGIS Pro. So I encourage you to take a look at this information for each of the rasters. It has a lot of descriptive text about that particular product and also links to other resources that can help you learn more about that particular product. ASF has developed a custom toolbox for use in ArcGIS. It is useful in either ArcMap or ArcGIS Pro, and you can download it from our website. Again, this link is listed in the persistent links pod in Adobe Connect. You go to our GIS tools section of our website, and there's a green button to download the toolbox zip file. Once you've downloaded that zip file, you can extract the toolbox anywhere that you want it to be on your computer, and then it will be available for you when you open your ArcGIS software. Just navigate to that location, expand the toolbox, and click on any of the tools to use them just like you would any other ArcGIS tool. It's important to note that the tools, almost all of the tools in this toolbox, make use of the Spatial Analyst extension. And so if you are using an ArcGIS product, you need to make sure that the Spatial Analyst extension has been activated. And if you don't have a license that allows for that extension, you'll need to either upgrade your license, or you can use QGIS. In this demonstration, I will be doing the actual demonstration in ArcMap using the custom tools, but each one of these processes can also be accomplished just using the tools that are available in each of these platforms natively. So I'll do a demonstration quickly with each of the processing steps in ArcMap with the custom tool, but then I'll return to the slide deck and we'll go through how you would do that manually with ArcMap, ArcGIS Pro, and also QGIS. If you don't want to upgrade your Esri license, you can always use QGIS. It's a free software package that is easily available. You can use it on Windows or Mac. It's very flexible, and you can accomplish all of these workflows with QGIS. The area we'll be looking at today is Midlands County in Michigan. There was heavy rainfall earlier this spring in this area, and it resulted in flooding and also a dam failure. So we'll take a look at the Shiawassee National Wildlife Refuge to map the flooding extent, and then also take a look at the Edenville Dam, which was breached after the heavy rains. The first tool that's included in the toolbox is actually a pretty simple utility just to unzip files. So if you're downloading a lot of products from Hype, you have a lot of zip archives that you may want to move to someplace else. The zip files are quite large, and they tend to have very long directory names. So if you're just using your regular utility, for example, just the default Windows unzip tool, if you don't specify a location to unzip the files to, you will often, the default is to put it in a folder that's named the same as the zip file, which makes for a very, very long pathway. And in some cases, it will exceed the number of characters that is allowed in a Windows path. So this is just a simple tool where you can enter the source folder that has all of the zip files, enter the destination folder where you want to extract them to, and then it goes through, looks for all the zip files in that first folder and extracts them all to the destination folder. At the same time, once the zip file is extracted, it will delete that zip file. So it sort of helps with file management and keeping your computer clean, because these files are very large. So in general, you don't need to have 2 copies floating around on your machine. The first thing we're going to do is convert RTC products to a different scale. RTC products are often output in power scale, which is a great scale for numeric analysis, but often visualizes poorly. If you were to bring an RTC product that was in power into your GIS, chances are very good that it will appear extremely dark or indeed all black. And that's because most of the values are going to be quite close to 0, but you may have a couple really bright scatterers that have a much higher value than all of the rest of the pixels. And just a few of those can really skew the range of values that are present in the raster. And so by default, it's going to show either the entire range or a % clip that still is going to be mostly values that are very close to 0. So you can deal with this easily by just changing the stretch and visualizing it differently. So in the properties, you can just set it to a standard deviation stretch of 2 or 2.5, and generally that's enough to be able to see the features. The data is there. Don't be concerned if your image looks all black. It's just a matter of visualizing it in an appropriate way. But there are some cases where you may want to do more than just visualize. In that situation, you're not changing the pixel values. You're just adjusting the way you're looking at those pixel values. In some cases, you may want to actually convert the data to a different scale. Two common other scales that are used for SAR data are amplitude scale, and this is not to be confused with the big A amplitude. We're dealing with amplitude data here, but these are just names for the scales for displaying the values. So there's amplitude scale, which is simply the square root of the power value, and there's the dB scale, which is 10 times the log of the power value. Amplitude scale is generally good for most numeric analysis as well, but also tends to give you a much better visualization. So if you were to bring an amplitude product into your GIS, probably it would display fairly well. For dB, this is a good scale for differentiating among very dark pixels. So if you're interested in delineating water, for example, and you want to be able to see clearly just the darkest of pixels, then dB is often a good choice. It does tend to wash out all the rest of the pixels, and so it may not be the best option for just a visualization, but it's good for identifying water or for looking at gradients in amongst the really dark pixels that are present in the image. Because it's a log scale, it may not be suitable for all numeric analysis, so just take care if you are running statistics on these data sets. dB scale may not always be appropriate for all statistical analyses. So I'm going to open ArcMap, and here we are in central Michigan. I've already used my unzip tool to extract my data from my HYPE zip archive. And what I'm interested in today is the VV layer. When I ordered the product from HYPE, I selected an output in amplitude, and that's indicated in the list of options. So this is a gamma naught amplitude product that has not had a speckle filter applied. So I'm going to add this VV layer to my image, or to my project. And you can see that the lake shows up very dark, and indeed all the surface water across the landscape appears as being very black. There are a few places that have some bright scatterers, and in general, that developed areas or cities tend to have a lot more bright signals. There are a lot of sharp angles and smooth surfaces that can easily reflect the signal back to the sensor. And so developed areas often will appear more bright than the rest of the landscape. In the rest of the area, there's sort of a range of grayscales. And because this is a VV layer, the lighter areas are going to be indicative of either a rougher surface or higher dielectric properties. Likewise, darker sections could either indicate a smoother area, so for example, a plowed agricultural field as opposed to a forest, but it can also indicate the dielectric properties as well. So soil moisture is one big driver of differences in the amount of backscatter. So a dry, smooth, freshly plowed field is going to have much lower backscatter than a moist field or a forest. I'm going to zoom in to the Shiawassee National Wildlife Refuge area. So this image was taken on the 15th of May, which was before the flooding occurred. I'd like to just show you some Sentinel-2 images. So this is an image from the 12th, which was also before the flooding. And you can see this area has a lot of standing water, and then there are fields that surround it and a community. The image from after the flooding, this is the first available image after the heavy rainfalls. This illustrates one of the issues with using optical data for trying to delineate things like flooding. There is a beautiful cloud bank right over the area that we're most interested in looking at. If you were to just glance at this image, you may not even notice that there was flooding that occurred in that area. So we have our SAR image. This is before the flooding. Then I'm going to add also an image collected after the flooding on the 27th. And you can see that there's no obstruction by the clouds, and you can clearly see that something has changed on the landscape. So the first thing we're going to do, I'm going to expand my ASF Tools toolbox and select the Scale Conversion tool. I'm going to convert these images from amplitude into dB. So I'll open my folder for the acquisition on the 15th of May and select my VV layer. I then need to define that it is in amplitude scale and that I want to convert it to dB. The default output folder is the same as the location of the input file, and the default output name is the same as the input name, just with an underscore dB tag. So you can change the defaults to be wherever you would like to output your raster, and you can change the file name as well, but I'll just stay with the defaults and click OK. You can see it running, and while that's running, I'm going to queue up the next one as well. So the post-flooding on the 27th, the VV layer from amplitude to dB, and click OK. Now that that's finished running, I'm just going to refresh my folder and add my DB products. So here's the VV for the earlier date on the 15th. And you can see already the water remains very dark, but the surrounding terrain is much more washed out. And then the image from the 27th of May, also in DB. All right, I'm going to return to the slide deck, and we'll go through how you would do this manually without using the tool. In ArcMap, you would open your search pane and enter raster calculator in your search. Select the raster calculator spatial analyst tool to open up the raster calculator interface. You need to have added the TIFF that you want to convert into your ArcMap project before you begin. And once it's in your ArcMap table of contents, it will show up in the list of layers and variables that are available. You can either type in or paste the expression that we'll be using, or you can access the log10 and the square functions from the list of functions. So you can scroll down below the math topic and select the log10 and the square. So it's log10 of the square of the amplitude value times 10. You select the destination where you want to save it, enter a file name, and make sure to add the .tiff extension. You click OK to generate your DB file. If you were working with power files rather than amplitude, you would just remove the square component. So it would just be log10 of the power dataset times 10. In ArcGIS Pro, you need to open your geoprocessing pane and enter raster calculator into the search. Open the raster calculator spatial analyst tool, and it's a similar interface. You enter your expression here. Again, you can select the log10 and the square from the list of tools, and then select the destination and name your output raster with the .tiff extension. Click Run to generate your DB file. In QGIS, the raster calculator is accessible through the raster menu. So you select the raster calculator, and it opens a dialog box that's very similar actually to ArcGIS products. There are a few syntax differences. So instead of typing out square, you use to the power of 2. So it's log10 of the amplitude squared times 10. Note that QGIS is also explicit about the band number. So the RTC files are a single band raster. There's just one band in there, but QGIS still tells you that you're working with band 1 of this particular raster. You can set the output location and the file name and select GeoTIFF as the output, and then click OK to generate your DB file. So the next thing we're going to do is look at these DB layers and create a water mask. So to do this, we can simply set a DB threshold between the darkest of pixels and all of the rest. And then we'll export a map that has just the water pixels included. So I'll return to ArcMap. And what we're going to do is start with our pre-flooding image, and we're just going to change the symbology. So if we right-click on the layer and select Properties, we can go to the Symbology tab, and instead of stretched, and again, this is where you can change from percent clip to the standard deviations or a minimum maximum that you set in order to be able to visualize the image more clearly based on what you're interested in. But we're going to move away from stretched and select classified. We're going to set just 2 classes because we're just interested in water versus not water, and then click the Classify button. This exposes a histogram of all the pixel values, and if you zoom in, you can see that there's kind of a small peak early on and then a larger peak with all of the rest of the pixel values. And this small peak tends to include all of those water values, all of the very dark surface water values. So we'll just move our breakpoint to be somewhere between those 2 peaks, and I'm just going to give this a round number. We'll say -17. Click OK. I'm going to set my color for my water to be blue and everything else to have no color. Click OK, and then suddenly you can see, so I'm going to compare with the original image before the flood. We've now created a water mask that covers pretty much the water that we can see. There are some areas that were not quite covered by this mask, so you may want to go back and adjust this value a little bit. You can set the threshold value and experiment to see what best represents your particular image. There's not one special magic number. It will depend on the conditions and your particular area. So now let's look at the post-flooding image, and we'll do the same thing. We'll set the classification to be 2 classes. And if we zoom into the histogram, you can see that the first peak is much more pronounced in this layer than it was in the last one. And that's likely because of all the surface flooding, which resulted in a lot more dark pixels throughout the image. So there's a much clearer delineation now between the two peaks. So we'll move this over. And so that's about -18. So we'll just go ahead and set it to be the same as the other one. Click OK, and then I'll set this to be orange for the water and no color for everything else. And if we rearrange those, we can compare. You can see that the difference between the original mask, the water from before the flooding on the 15th is in blue, and then after the flooding, water extent is in orange. So all we've done here is change the visualization of the raster. If you were to add this DB raster into any other project, it would just be a stretched grayscale image. So we may want to actually export a completely different raster that only includes the pixels that indicate water. And so to do that, we can use the RTC Reclassify tool. I'll select my DB image, and it will default to save in that same folder, and it tags, the default is to tag it with reclass. If you want, you could add a note to yourself of what your threshold was in case you want to generate a number of different alternatives to look at to see which one gives you a better water mask. And then I'll just enter that same value that I used for my breakpoints. In this example, we used -17. So I'll enter that and let it process. I'll refresh my folder to see that new layer and add that to the project. And you can see that shows exactly the same thing as the original DB that we just changed the symbology. But if I was to look at each one of these pixels, you can see that all of the water pixels have a value of 1, whereas everything else just has a value of no data. So you could add this to any project and it would just show you the extent of the water. And you can use that for analysis, either multiplying things by this mask to determine what's water and what's not, or if you just wanted to have a visualization that you added on top of other layers, it could show, you could do a variety of masks through time and just show the progression of the water inundation. So I'll go back to the slide deck and we'll talk about how to do this manually. To reclassify in ArcMap, you would open your search pane and enter Reclassify and select the Spatial Analyst Reclassify tool. That opens this interface and you select the input raster and then click the Raster Classify button. This opens an interface that looks pretty much exactly like what we were working with when we did just the visualization and change the symbology. So again, you can move the line or just enter a break value, set to 2 classes, of course, and then click OK. And that changes the table so that it only includes those 2 classes. You can set the new value to be 1 for water, and then no data for all of the rest. Or you can also choose other values. If you wanted to have your water be 0 so that you could multiply it by other layers and set anything that's under that water mass to be a 0 value, you could do that. Or if you wanted everything else to be 0, you could also enter that instead of no data. It's your choice. You would scroll down and enter the output location and file name with the .tif extension and click OK to generate the reclassified RTC layer. In ArcGIS Pro, you'd open your geoprocessing pane and enter the Reclassify to search for the Spatial Analyst Reclassify tool. Select your input raster and then click on the Classify button. You enter the number of classes to be 2 and click OK. And then you'll need to enter the breakpoint in 2 different locations. First, you'll need to enter it for the end and for the start. And I should clarify that in our example that we did in ArcMap, I used -17. In these examples, it's -13.5. It just whatever breakpoint you decided was best for your particular application, you can enter that. So you would enter that value for the end and also then for the start of the next class. And again, you can select the values, 1 for water and no data for not water, or whatever other values you would like to assign to those different classes. Set the destination folder and a file name with the .tif extension and click Run. In QGIS, this functionality is found in the Processing Toolbox. So under the Processing menu, select Toolbox, which opens this interface. You expand the raster analysis option and click on the Reclassify by Table. This opens this second dialog box where you select the raster layer, and then under the Reclassification Table option, you click on the ellipses to open the Fixed Table window. You'll need to click on the Add Row button, and then you enter the minimum value. If you know the minimum value, you can enter it directly. Otherwise, you can just use -INF for -infinity. And then for your breakpoint, for the maximum, you would add in that break threshold and set the value to 1 or whichever value you want to use for that class. You'd click Add Row again, enter in the breakpoint, and then put infinity or the maximum value under maximum. For QGIS, if you want no data values, you can either use -9999, or you can also use the letters capital N, small a, capital N for not a number. Or you can also use an integer value here if you prefer. You click OK, and then by default, QGIS just generates this as a virtual layer, so it's only in that one project. If you actually want to save it out as a raster that you can access in other projects, then you'll need to click on these ellipses and click the Save to File option, and then you can select a directory and give it a file name and save that out for use elsewhere. In general, if you add this into your project, you may find that it visualizes in just a grayscale stretch, which may not be what you want. So if you want to change that, you just right-click that layer in the table of contents and then select the item properties and go to the symbology section. For the render type, select paletted or unique values, and then click the Classify button. This will add all of the different classes that exist in the file. In this case, there was just one class, water, and at that point I can change the color to be whatever I want and click OK to set the symbology. So the next thing I'd like to go over is calculating the log difference between files. So just looking at the log difference, which is the ratio of the log ratio between the earlier or the most recent, sorry, the log of the most recent acquisition divided by the earlier acquisition can really show you areas where change has occurred. It can sometimes be hard to just notice change visually just by looking at a grayscale image or two grayscale images, but by doing a log scale, you can it often really pulls out areas where the values have changed significantly. All right, so we are going to move up into the Edenville area and look at the region that had the dam breach. So if we look at the RTC, there's this large black area, and that's the reservoir above the dam. So this image is before the flooding, and then we still have our mask showing from after the flooding, and you can see that there was a lot of difference. We lost most of the water in this area, so all that's left is just a very small amount of water. So we'll turn that off and select our Calculate Log Difference tool. So we'll enter our most recent acquisition. So I'll select from the 27th of May. And I should clarify that this tool is best used with amplitude datasets, although power is also okay. I don't recommend using it with DB because DB is already in a log scale, so you're applying a log to a log. So we'll choose our amplitude VV layer, and then we'll select the earlier acquisition from the 15th, and again, select the amplitude layer. The destination default is the same folder that has the newer layer, but I'm just going to change that to be my base folder. The default output name is just the earlier granule, the product name, and then the newer product tagged with a log difference. So I'll click OK and let that run. And then I'll refresh my folder. And here's my log difference file. I'll add that to the project. And you can see that in this case, even in grayscale, it's very obvious that something happened here. In most cases, the changes may not be this clear. So there are a couple different ways that you can make changes sort of pop out a little bit better. The easy first step is to just change the color ramp. Instead of being grayscale, you can change it to a color, and sometimes that helps the differences pop out visually a little bit more to our eyes, but that still doesn't tell you anything about the quantification of the amount of change. So we're going to go back, right-click, and select the properties for that layer, and go back to our classified symbology. We'll leave it as 5 classes and click the Classify button. I'm just going to zoom into the histogram a little bit here. So if there was no change from the first date to the second date, you would expect a value of 0. So in this case, I want to have my breakpoints be set around 0. And I'll often use the standard deviation as kind of a guide for where I put my breakpoints to start with. So I'll just give a value of minus 0.15 and a value of positive 0.15, and then 0.3 and negative 0.3. So you can see that most of the pixels fall within minus 0.15 and 0.15. So these pixels likely underwent very little to no change. If we look at the histogram, though, it's very clear that in this particular image, most of the change that was beyond, most of the actual change was in the negative direction. So that means that there is less backscatter in the newer image than there was in the original image. There are still a few pixels over here on the right side that indicate that there was a positive change, but the vast majority are over here on the left side of the histogram. So I'm going to click OK, and I will apply a color bar. And this makes it very clear where there has been significant change on the landscape. So this region that shows up in bright red is that reservoir that largely drained after the dam was breached. So because there was this indicates a positive change, that means that the backscatter values are much higher in the more recent acquisition than they were in the original acquisition. And this makes sense because in the original acquisition, there was that big reservoir that had all that flat, calm surface water, and that just bounces the SAR signal right off it, away from the sensor. It has extremely low backscatter returns. Whereas once that drains, what's left behind is saturated soil. And because water has a high dielectric constant, if soil is saturated, it can reflect a lot of the radiation back to the sensor. So the backscatter results from a saturated soil are going to be much higher than from surface water. So that shows what's happened here. We've had that very large increase in backscatter with a movement from an area being covered with water to being just saturated soil. We're going to move back down to our Shiawassee National Wildlife Refuge area. And here we see that there are a lot of really dark blue sections. And because we mapped the flooding in this area, we know that these are likely regions that underwent flooding from before to after. Now, it's important to keep in mind that there is more than one thing that can drive a decrease in radar backscatter. In this case, because we're aware of the flooding, we can assume that these areas are darker because there's now standing water. Before there was soil, which is going to have a much higher backscatter than standing water, but it went from a brighter return to a darker return once it was inundated. So suddenly you have standing water above those fields, which has very low backscatter return. So you've had that decrease that was caused by the flooding. But another possible driver of a decrease in backscatter can also be drying. So dry soil, it returns much less backscatter than wet soil. So if you had a really, really hot week and you went from having quite moist soil, especially with a C-band sensor, it's getting returns from pretty high up in the soil surface, which can dry out fairly quickly. So if you've had a serious drying trend over your week, that could also indicate significant changes in the negative direction. So you could have much less backscatter, and it's caused by exactly the opposite thing. In this case, we're having more water, and in the other case, we have less water in the system. So when interpreting SAR data, it's really important to have some context about your site and understand and be able to make the proper assumptions when you're looking at these data sets. I'll just zoom out quickly to the entire extent of the RTC, and you can see that this bears out the histogram. Most of the change that happened on the landscape is in the negative direction. So in most cases, you had a decrease in the radar backscatter over that time, with a few exceptions, such as that dam area. So I'll return to the presentation, and we'll go through how you would do this manually. So in ArcMap, again, you're accessing your raster calculator. So search for your raster calculator, open that up. You need to have both of the images that you want to compare already added into your map. And then you just take the log of the newer acquisition divided by the older acquisition. You'd set your output raster location and file name with the .tif extension and click OK to generate your log difference file. In ArcGIS Pro, you would search for raster calculator in the geoprocessing pane. And again, enter the log of the newer granule divided by the older product. And select your output location and the file name and set the .tif extension. Click Run to generate your difference file. In QGIS, the raster calculator is found in the raster menu, and similar to ArcGIS products, the log of the newer product divided by the older product. Set your output layer location and file name, save it as a geotiff, and click OK. Before we wrap up, I do want to go over a couple of other options that you can use for getting RTC datasets. So I mentioned that these datasets that I worked with were from HYPE, but you can also process by yourself using the Sentinel-1 Toolbox. The Sentinel-1 Toolbox is provided by ESA to work with SAR data, and it's a very user-friendly interface, but it can do a lot of things, and it can be hard to know which processes you actually have to use to generate an RTC product. And so we have a data recipe, and the link for this again is in the persistent links pod in the Adobe Connect presentation. This data recipe takes you step by step through how you would take a GRD, a Sentinel-1 GRD, and convert it into an RTC product. So that way you can do it all on your desktop. Another option, which I mentioned on Tuesday, is that the PALSAR-1 mission from JAXA, the Japan Aerospace Exploration Agency, all of the holdings that we have for that mission have been already processed to RTC, so you can download them directly from ASF's Vertex data search portal. You would just select the dataset of ALOS PALSAR and enter your area of interest, enter your start and end date, and then click on the additional filters to select just the terrain corrected products. The high res are in 12.5 meter and the low res are in 30 meter resolution. And so you can search for those, download the ones you're interested in, and they're ready to go. You can just bring it into your GIS without any additional processing at all. This mission ran from 2006 to 2011, and it's an L-band mission. So just be aware that it's a very different data set than Sentinel-1, for example. At the last webinar, I noticed that a lot of people in the feedback requested the ability to use a shapefile when using Vertex. And so I just want to mention that that is supported in our Vertex data portal. So if you're interested in using your own shapefile to delineate your area of interest, you can just select the more options and import the area of interest. And you can just drag a .shp file. All we need is the .shp, or you can drop the entire zip folder of all of the shape file, all of the different files that comprise a shapefile, but all we need is the shapefile. There are a few caveats. It needs to be in a geographic coordinate system, so you can't have it projected to UTM or Albers or any other projection that you may use. It has to be in latitude and longitude, so either like WGS 84 or NAD 83 or something similar. So you can use that, and then it populates your area of interest just directly from your shapefile. You can also use a GeoJSON or just well-known text if you want, or there are also a couple of options. You can either draw a square over a particular area, or you can draw a more complex polygon. The other cool thing is that if you've generated a polygon in Vertex and you want to use that well-known text elsewhere, for example, if you were using HYPE and you wanted to enter use that same area of interest for your HYPE subscription, you could click on this copy to clipboard, and that copies the well-known text. So if I paste that, it has all of the vertices that are included in that polygon. So I just wanted to let you know that that functionality is supported. So if you're interested, be sure to check that out. And with that, I will pass it back to Jennifer.
Okay, thank you, Heidi. Thanks, everybody. At this point, we'll transition to our final optional set of polling questions. We're going to give these about 4 minutes or so, 3 to 4, and then we'll move from there directly into the question and answer period. All right, so thanks everybody. We'll give these a few minutes and then we'll jump right into the question and answers. All right, thank you. Okay, everybody, at this point, let's transition to our Q&A period. But if you think of something, feel free to jot that into the Q&A pod. We'll try to get to all of our questions during the Q&A, but if we do not, our speaker will follow up offline in the next few days or so. All right, so our first question is, can level 0 data be processed in height?
So we would not choose to process level 0 data because ESA already provides GRDs and SLCs. We always start from that because it's already, a lot of the processing lift has already been completed by ESA. So when generating height products, we start from a GRD. If you were to select raw data, we would just use the GRD or SLC depending on which product would be more appropriate.
Okay, thank you, Heidi. Our next question is, a moist soil shouldn't appear brighter on cross-polarization due to dielectric constant resulting in electromagnetic interaction, should it?
Oh, sorry, I missed the first part of the
Sure,
question?
sure. It's okay. A moist soil should not appear brighter on cross-polarization due to dielectric constant, resulting in electromagnetic interaction, should it?
That's an interesting question. So if you have a higher dielectric, if you have an object with higher dielectric properties that's also a volume scatterer, then that's going to be at play. So the cross polarization is only impacted if a volume scatterer is at play. So in order for the signal to be changed in its polarization, it has to interact with something other than just a regular surface. So hopefully that addresses the question. It's there's still, both things are at play, but there also has to be that component of the scatterer needs to be some sort of volume scatterer for you to get higher results in the VH returns.
Okay, thank you, Heidi. The next question is, I'm actually going to summarize so that it makes sense as a question. So can you talk a little bit about the coverage for the data from, so for example, from 90 degrees north latitude to 90 degrees south latitude? This person is actually from Brazil, so they're trying to, obtain a bit more information about coverage.
Sure. I'm just going to bring up for myself the vertex area. So is this specific to Sentinel-1? Was that, or in general?
So that information was not provided.
Okay. Well, so for polar orbiting satellites, it will depend on the direction that they're looking. So if it's a right-looking satellite, it'll get better coverage of the Arctic and less coverage of the Antarctic, or that may be the other way around. I'd have to think about that. But depending on the look direction, you'll get one pole better than the other. But the actual data coverage is pretty much unless you're really concerned mostly with right at the poles, you're going to have global coverage. In terms of RTC, if you're using our HYPE platform, it will depend on the availability of publicly accessible digital elevation models. So currently, we use the SRTM, the Shuttle Radar Topography Mission DEM, and in North America, in many areas, we use the National Elevation Dataset from USGS or the 3DEP products. And so in North America, pretty much we have full coverage with the NED. And elsewhere in the world, we have, it's between 60 and 60 north and 60 south latitude. So if you're within that area that was covered by the Shuttle Radar Topography Mission, then we can generate HYPE products or RTCs. If you have a digital elevation model for your area, there should be coverage by Sentinel-1. Certainly in Brazil, there's great coverage with Sentinel-1 and many of the other missions as well. For the larger satellite missions, we'll have acquisitions over that area. And there is coverage by the Shuttle Radar Topography Mission, so that shouldn't be a problem to process that data to RTC. And if you have your own DEM, that's even better. You can use that if you're working in Sentinel-1 Toolbox or processing on your own. You can use your own DEM. So generally, it's going to be the DEM that's more of a limiting factor than the actual data acquisition, unless you're right at the very pole.
Okay, thank you, Heidi. Our next question is, what about letting machine learning find the peaks with the histogram being a mixture of two distributions?
Sure, and actually you wouldn't even necessarily need machine learning. You could just do a statistical analysis of those two peaks, and absolutely, that's a very valid way of finding that value between the water and the rest of the pixels. And if you wanted to program that into a workflow, certainly that's going to be a much easier way for automating that process than if you are visualizing each one. For today's demonstration, I just wanted to show you that it's pretty easy just to visualize it even. And so if you're not interested in doing that intensity of programming or don't have the statistical background, you can still be delineating the water. But certainly there are methods to determine the appropriate point between those two peaks.
Okay, thank you, Heidi. So our next question, and I'm not sure whether this might be something you need to follow up with offline, so let me know. So it's actually two separate questions I'm going to combine into one. How do you calculate the water area and the height of the water? Or can you calculate the height of the water using these data?
So in terms of the height of the water, that's an interesting question. So the elevation data would be coming from the data set. If you're trying to, so area, if you project, if you've got your water mask or you've created that raster that only includes water, you can do all kinds of analysis on the area that's covered by water pixels. If you have just one area you're interested in, you can draw that, and as long as it's projected to a suitable projection that doesn't have distortions in area, so like an equal area projection or UTM in the appropriate zone, you can calculate the area of the pixels that have a value of 1, for example. So that's very easy. Looking at the area changes with SAR is very straightforward. Looking at the water depth of a reservoir is going to be different. So if you have lakes that have very shallow sides, then often you can use the area of the lake as a proxy for how full the lake is. But in a reservoir that has a really steep side, you're not going to be able to see very much difference. Because the height values in the RTC are coming, that's only based on what the DEM says. So it's not interactive at that moment. It's just whatever the DEM calculation for the height of that surface was whenever the DEM was generated. So with this process, it's not, there are other things that you could do to determine the height of the lake, but not just using this visual approach. But as I said, if you're looking at a shallow lake where you can, if you've got a gauge that you can set a correlation between the water depth and the surface area, if there's a good correlation there, then it's a great way to keep track of the movement of water up and down because you can track that just by surface area. But it'll be really site specific on how that works. Was that both questions?
Yes.
Okay.
Okay, so let's see here. This is a question about DEMs. How can I get altimetry data?
Altimetry data, so there are other DACs that specialize in that more. So NSIDC probably has a lot of altimetry data sets. I would have to look up specifically which altimetry data sets are available.
Right, so there are, there's the ASTER Global Digital Elevation Model at LPDAC, and I'll type their data center page into the Q&A pod for you. So the next question is, what are the best satellite products for measuring inundation depth?
Oh, inundation depth, that's a good question. So water is tricky to sense through because it does have such high dielectric properties. And there are bathymetry sensors out there that can actually determine in kind of more shallow areas, can determine lake depth, but that's not an application that's inherently suitable for SAR data sets, if I understand the question correctly.
I believe so. If there are additional points of clarification, our user will need to type that into the pod. The next question is, how do you co-locate the various images?
I would like some clarification on that question. Maybe they can get in touch. In general, so the Sentinel-1 images, for example, the GRDs have already been georeferenced by ESA, and there are very accurate location data for the Sentinel-1. Like, it really knows where it is all the time. And so the Sentinel-1 data sets are very well georeferenced. And so if you're looking at a GeoTIFF or a GRD, that will be very close to where it should be on Earth. So you shouldn't have to do anything else. I mean, the terrain is going to be the biggest problem, and so the terrain correction is what drives how well it interacts with other features, or how well it aligns with other features from other data sets. But in terms of the actual placement of that granule on Earth, it's pretty good. And the Sentinel-1 Toolbox, in fact, when it does RTC, it just assumes that it's in the right place on Earth. There are some other processing softwares that can kind of move things around based on the DEM. So if you are more confident in your DEM than you are in the satellite data, then you could adjust it based on that. But often DEMs are not really, unless you have a really high quality local, maybe you had some LiDAR run to generate a really high quality local DEM that you trust. In that case, you may want to use that to locate the actual features in the image. But in general, you're probably better off going with the Sentinel-1 georeferencing, if I understand the question correctly. I'm not clear on what what things want to be co-registered. So.
Sure. And I just want to make a note to everybody that I'm going in order of the questions as they were received within the Q&A pod. So if we don't get to your question, it's not that we are ignoring it, it's that we didn't make it that far. And our speaker will follow up with you offline. The next question is, and Heidi, for reference, you were discussing radar backscatter using the ArcMap during that demo portion of the webinar. Is this method, and I don't know if this will be enough information, is this method also applicable for the estimation of forest dynamics, excuse me, as for example, forest biomass change? Did you hear me okay?
I missed a few of the words, but SAR can be used for calculating forest biomass in some applications. Let's see. I don't think I have a link to the SAR handbook, but there is a SAR handbook that's been published that is pretty specific, actually, to forest biomass applications. And so I will see if I can find that link quickly and add that in. But it's a great resource if you are interested in more the forest biomass estimation. So I have that here. I'll just send that to Jennifer to post.
Okay. All right. So the next question is, how do you deal with all of the noise? I am interested in preserving resolution while also filtering.
Right. So filtering is always tricky, and it can really depend on your specific location. So speckle filters are a valid choice. We often default to the enhanced Lee filter, but how big you want your window and how much play you want in that filter, how much filtering you actually want to do, can really change your output. And so if you're working with filters, it often comes down to experimenting with the filters that work best for your particular application. Sometimes, so that's something that you can apply if you're just looking at a single image and you want to get rid of the speckle, which is inherent to SAR data sets. That's part of the nature of the data set. Is sometimes you'll have bright pixels where you don't expect them, and the opposite way as well. So another option, if it depends on your application, but sometimes you can filter things temporally as well. So if you're interested in like the monthly average of lake area, for example, if you have 4 or 5 images from the same area within that month, sometimes just averaging those together actually takes care of a lot of that noise without losing a lot of the information. And so depending on your application, it can be worth a try. This is, of course, not going to work if you're interested in capturing the information from just one date. But if you're looking at more like trends, and you can either use a rolling average where you had 4 images at a time averaged together and then moving forward with that window with each acquisition, that can often help with the filtering without losing the resolution of the actual features themselves. So depending on your application, that can sometimes be a helpful approach.
Okay, thank you, Heidi. Moving on to our next question here. Can you briefly explain P-band and its application and what satellite sensors provide P-band? Excuse me.
Yeah, we have almost no P-band data in our collection, and I've never actually personally worked with P-band data, so that would be a question I'd have to pass along to somebody else.
Okay, thank you. So there were 2 questions regarding the part of the demo when you were looking at the lake. The first question is, why is there an increase in the backscatter in the lake to the northeast? Calmer water?
Right. Yeah. So VV polarizations are very sensitive to roughness, and so this is an issue if you're looking at large bodies of water, because on windy days, the backscatter can be really a very different signature than on a calm day. So it probably has more to do with the actual physical conditions of the water surface than anything else. It's probably driven by it was a windier day on one of those acquisitions than it was on the other one. So it doesn't have to do with flooding or anything like that. It's probably driven almost entirely by that surface roughness.
Okay,
so if you were interested, yeah, I'll just go to go a little bit further. If you're interested, so the data set that you choose to use will be dependent on what you're interested in looking at. So I was interested in the still water that was not on the lake. And if you were to do like a water mask for a large lake, you may find that you would need to use a different threshold than you would for a creek or a small lake as well. So just because you have an entire RTC image, you may not be able to apply just one single threshold to the entire image and be able to capture all the water, because there are different things at play. So for example, the lake that was part of that image would not have met the criteria for most of those, for that threshold. Most of the pixels would not have actually been classified as water. But if you upped your threshold, then you would start getting false positives over land as well. So you need to be a little bit careful when you have such different features all in one RTC image, and definitely focus on the part that you're interested in knowing about. So I didn't care about the lake, so I wasn't trying to choose a value that was appropriate for creating a water mask for the lake. So yeah, it all depends on what you're interested in learning.
Okay, thank you. The next question was, why is the lake also indicated as an area with negative difference? Because there was already a water body present before the heavy rain?
Yeah, so this goes back to that same surface roughness. So if it was, if there's less, it just means that it was a calmer day probably that second day. Maybe on that first sunny day, it was windier, so you had higher backscatter. And then if it was a calmer day, you're going to get much less backscatter, which would drive, again, a decrease in the backscatter.
Okay. Give me just one second here. Okay, so the next question, which we probably only have time for this question right now. So this is when you were focusing on the vertex demonstration, and the question is, can this toolbox be used to calculate land subsidence or upliftment using SAR imagery?
So I'm not clear on the vertex versus ArcGIS question. So in vertex, there's no analysis.
There's no ArcGIS in this question. You were at the time that this question was asked, you were going through a vertex demonstration, and the question is, can this toolbox, or I guess can vertex, be used to calculate land subsidence or upliftment using SAR images?
So Vertex is not an analysis platform. So Vertex is simply a data discovery and download interface. So you can't actually do analysis within the Vertex platform. You can go and find data sets and download those data sets, but there's not an interactive analysis component to Vertex. We do have some, if you're looking at subsidence and uplift, that's more an INSAR question. So that's not something that would be addressed with the amplitude part of the data set. That would be a phase question. And you could look at some of the interferograms that we have available and see if they give you the information you need, but there's not an interactive way of doing calculations within Vertex.
Okay, thank you, Heidi. At this point, what we will do, I was going to upload the slide deck from the first webinar because we've actually had several individuals ask for that. So you should see that uploading in just a moment. And for those questions that have not been answered, I will be sending the Q&A log to our speaker. So she'll be able to follow up with each of you offline. Please don't hesitate to reach out to her directly. You can always email me as well, and I can forward any inquiries along to Heidi. I'd like to thank all of you for joining us today. At this point, what we'll do is we'll log off from the audio component of today's webinar. However, I will leave the virtual meeting space open for an additional 10 minutes for those of you who might be interested in downloading the first slide deck. And in fact, let me wrap up with that. You should be able to see it now. In the bottom right-hand corner of your screen, you are going to click on either one of those two PDFs, and you should be prompted with an option to download the files. And as a reminder, today's webinar was recorded. I will be sending recording links to all of the registrants for both Part 1 and Part 2. If for some reason you don't receive the link, please feel free to email me directly, and I will be happy to send that along to you. So with that, we will log off from our audio component and leave the virtual meeting space open. Thank you, Heidi, and thanks to all of you for spending the last roughly hour and a half with us. We appreciate it. Okay, take care, everybody. Bye-bye now. Thank you.